Another way of writing it. Sorry, this kind of looks like a zeta. This is an epsilon here. So epsilon, epsilon, epsilon sub zeta naught plus 1. But what if we wanted to stay in Veblen notation? So if we wanted to keep on going with this and keep expanding out. Because if we change it over to this and then start trying to evaluate this, it's going to get really messy. So what do I have here? Oh, I have 2. Yeah. Okay, so instead of switching over to this kind of notation, we're going to stay in Veblen notation. So how would we do this? Basically, first thing I do is I keep 2 copies of this here, and then I break one off. So I could do phi2, 1, and then break one off here. And yeah, I'm just going to, sometimes I'll do a bunch of steps in my head at once. I'm just going to keep this simple, just so I don't want people to get lost here. Phi1, and then I'm just going to rewrite what I had on the inside or whatever. So the only thing I did in this step was I broke this 3 into 2 copies and then 1 copy. So you're allowed to do that. Okay, so I have that. And then once I have this here, what I can do is I can break this here into 3 copies of the 0th function. So let's do that. So we keep this here. This is still in the beginning, so that stays where it is. Then we're going to break this apart into 3 copies of the 0th function. And then what we have to do is we have to keep this function here. And remember how we minus 1 from the inside here? So if you see in this rule here, we have to minus 1 from the inside and plop it out on the outside here. So now this whole thing is our inside. So we have to minus 1 from here. So we're going to minus 1 from here. So we can just get rid of this plus 1 here. That's nice and easy. So this minus 1 is just going to be this part here without this here. So we're going to write that down. So we're going to have phi1, because remember this is still part of the thing that we have to rewrite. So phi1 of phi2 of 0, this minus 1, we're just going to close that bracket here because phi2 of 0 plus 1 minus 1 is just phi2 of 0. And then we're going to plot this on the outside of this function here to escape the fixed point trap. So now we're going to get this plus 1 closed bracket. So you can imagine this whole thing is inside of this function here. Okay. And then, and then that's all diagonalized by 3. Okay. Now what can we do? Basically, let's do the same thing we did here. Let's break off 2 phi zeros and we'll keep 1 or whatever. So now we have that. We have 2 of the 0 ones, and we're going to break off a phi 0. So now we're going to have phi 0, phi 1, phi 2 of 0. And now something kind of funny happens here, because we have phi naught of this whole thing here plus 1. Well, as we saw here, phi 0 of anything is omega an exponentiation. I can't say that word. Wow, Jesus. Okay, an exponentiation. So if we have a phi naught here, basically we're going to take omega to the power of this thing here. And then if you remember your rules of exponents, omega to the power of a plus 1 is going to equal omega to the a times omega, right? That's just a general rule of an exponentiation. So now we're going to have omega to the power of this thing plus 1, which is the same as saying we have omega to the power of this times omega. So let's write that down here. I'm just going to erase the couple first rows so we have some room to write that down. So another way of writing this down would be, okay, we have all our stuff in the front here. So we have 2 copies of the 1 function, 2 copies of the 0th function. And then we have phi 0, phi 1, phi 2 of 0. And then we have this plus 1, But now we're going to close this bracket and we're going to multiply this by omega using our rule of exponentiation, basically. But now what can we do? We can take this omega and now we can finally diagonalize this. Because for the same reason why we can only diagonalize when there's a free omega, now there's finally a free omega at the end of this function, so we're allowed to diagonalize this. As long as there's nothing in between this number and the omega, we're allowed to diagonalize. So now we can turn this omega into a 3. So if you can imagine the bracket ends here, so I have this many closed brackets here. So this 3 applies to this whole function right here. So we have 3 copies of this. So now we can go all this stuff in the front here. We're going to have this, that, v2 times 0. And what I'm going to do is I'm going to keep 2 copies of it. And then I'm going to add the 3rd copy. And the reason why I do this is because we want to further break this down. So after this, I'm going to put a plus sign, and I'm going to add this thing again. Because I'm doing 3 copies of this, so I'm doing 2 copies down here, and another copy down here. So I'm going to add on this to 2 times this. So phi 0, phi 1, phi 2 of 0. This is diagonalized to 3. Okay, so now I can diagonalize this here. I can attack this. I can break this apart into 3 copies of the phi 1 function. So let's do that. So this is all going to stay the same. Like this is way back in the function. We're not going to be able to break any of this apart until we deal with this here. So I'm just going to rewrite just this little part here because I don't want to keep on rewriting this. It just wastes time. So I'm going to put this last part of the function here. So phi 0, phi 1, and we're going to break this apart into 3 copies of the phi 1 function. So 3 copies of phi 1 of 0. Okay, but now we can do the same kind of thing we did before. We want to break this apart further. So what if we keep 2 copies of the 1 function? Sorry, hiccup here. And then we break 1 off. So that's the same as saying we have 2 copies of the phi 1 function, and we're going to write a lone phi 1 function here. Okay. Well, now we can break this apart into 3 copies of the phi 0th function. So let's do that. So we're going to do 3 copies of phi 0 of 0. And we know from before that this is equal to omega to the omega. Because the same kind of way that we figured out what epsilon naught diagonalized to 3 was, this is the exact same thing. So phi 0 of 0 is going to equal 1, phi 0 of 1 is going to equal omega, and phi 0 of that is going to equal omega to the omega. Okay, well now we can diagonalize this omega here to get omega cubed. And if you remember from way back when we did a full-out expansion of that, this eventually turns into, so if we start with omega cubed, we break this apart into 3 copies of omega squared, blah, 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 blah. And eventually you get to omega squared times 2 plus omega times 2 plus 3. So that's how we break apart this ordinal here. And we've done that before, so that's nothing new. So we can rewrite that. And remember, I'm not going to rewrite the beginning of the functions. Like the function is actually larger than just this, as I said before. I'm just rewriting the last little bit of the function, or whatever, just because it's just easier. Okay, so the last little bit of the function was phi 0, phi 1, 2 copies of phi 1, and then we had that omega squared times 2 times omega squared plus 3. So now if we wanted to go on from here, basically what we could do is we could break off in omega 1. We could use this rule here to turn that into 3 copies of omega naught minus 1 from the 3, so this would turn into plus 2, and you could add it to the outside of the bracket. So basically it's using the same rule, and it does get a little bit complicated. You kind of have to really think about what you're doing when you're doing this to keep track of where you have to minus out a number and then add another one. But the rules always stay the same, and you always have this kind of nice, neat bracketed type of thing. You don't have this crazy like amounts of exponentials where you have to keep track of where everything is. It's a very, very neat way of doing this function or whatever, and it's a lot easier it's a lot easier to get lost in the other way. Let's just put it that way. But it still can get a little bit cumbersome. So we're gonna stop there for this example, whatever. I think we've kind of done that one to death. And let's see what else we can do with Veblen functions. Okay, so another thing that's allowed, kind of similar vein to what we did before, we can also plug in an infinite ordinal into the subscript of the Veblen function. So we can go phi omega of something. So let's see an example of this. So phi omega of 0 is pretty simple. We just diagonalize. So this is going to turn into phi 3 of 0. Yes, okay, phi 3 of 0. And if we have a number in here, the rule changes a little bit, so we have to do something to get out of the fixed point trap, just like before. But it's a little bit different. It seems a little strange, but this time, when we diagonalize this, we don't do 3 copies of the function. We just do one. Because if you remember, in this one here, we had to do 3 copies of the previous phi function, and then have the inside bit there, and the +1 to get out of the fixed point trap. But when we have an infinite ordinal in here, basically we're going to replace the first one with the 3. So we're going to diagonalize, so phi 3 of, we keep this function, so phi omega minus 1 from the inside, so we have 0, and add it to the outside. So really the only difference between this and a finite number here is with a finite number you put this many copies of the function, and then this. When you have an infinite ordinal, you do the same thing, but you just don't do the number of copies. It's just 1 copy of this. So it's a little bit simpler even. I think I'm going to leave that for this video. We're going to do more of the same thing, but I think this is a good time to stop. So we'll do more in the next video.